All right, in this lesson we're going to look at what happens when we have electricity and magnetism working together. So we already know that there's some similarities. Electric fields, magnetic fields are very similar. And we know that from the domain theory that if we have a electron spinning or any electron moving, that's going to induce a magnetic field. So there's got to be some sort of connection between the two. And what happened in 1820, Hans Christian Ørsted, he did a bunch of experiments to show that electric currents, any electric flow, could actually create a magnetic field, and it would affect the magnet doing it. So he actually basically sort of stumbled on this by accident in stories that I read. So basically, if we imagine we just have a wire, so we have some sort of wire and we got current flowing through the wire, what Ørsted noticed was, just by fluke, he had this wire set up and he happened to have a compass nearby, and he saw that the compass needle moved every time he turned on the current. So when he hooked it up to a battery and we got electrons flowing through the wire, he noticed that the compass needle moved depending on where it was located. So what he did was, if he put the compass needle to the like on top of the wire, he got that the magnetic field, the compass pointed to the left. And then he found that if you put the compass underneath the wire, on the bottom of the wire, he saw that it pointed to the right. And then when he put the compass to the right of the wire, nothing happened. But if you turn the compass so it was sort of perpendicular, he saw that the compass ended up pointing upwards or out of the page. And we're going to get to these symbols in a second. And then the same thing on the other side, he saw that it went downwards. So as he went around the wire, the compass needle sort of changed accordingly. So what he concluded was then that the electric wire created a magnetic field, and vice versa. If he took the electric wire and switched it around so that the current went the other way, what he found out was that the magnetic field switched directions as well. So he was the first to sort of connect the current to a magnetic field. So we're going to do a bunch of different hand rules to help us figure this stuff out. So the first rule is going to be, how do we know which hand to use? So we're going to use, for anything that has to do with negatives, so we have electrons, electron flowing and current, or basically anything in general that's negative, we use our left hand. If we're dealing with something that's positive, so we're going to have protons moving, or we're going to call it conventional current, anything like that. You see that in a question, anything that's positive, you're going to use your right hand. So we're going to use the two hands, one for positive, one for negative. The second thing we got to do is we just got to be careful of our directions. So we're always going to use directions as referred to our paper. So if you're drawing on your paper, we would say the top of the page is north or up, right? Up as being the top of your page. The bottom of the page would be south or down. And we'd say the right of our page is east or to the right. And then our other side would be left or west. Okay, so we're always going to do it in reference to you drawing it. So on paper, if you were to draw up, that'll be our north, left would be west, and so on. But then we also have, because now with magnetic fields being perpendicular, we got to worry about three-dimensional directions as well. So what we're going to say is coming out of the page, so upwards, not up, but coming out of the page towards you, we're going to use the symbol, a circle with a dot in the middle. Okay, so that's outwards or out of the page. Or towards would be another way of thinking about it. And then we're going to use an X to show into the page or away from you. And the reason they use a dot and an X, it's sort of representing an arrow. So if you were to shoot an arrow at somebody, the dot would be coming towards you, right? You'd see the arrow coming towards you, you'd see the point of the arrow. And if we shoot it away from you, we'd see the back of the arrow, the feathers of the arrow, which would be the X. Okay? On this page, I've got these 1, 2, 3, 4 numbers listed. This is off a diploma, and this is how sometimes they'll test you on direction. So they might give you a diagram and say, what is the direction of the magnetic field at a certain point, and you'd figure out the direction and you would answer it as being 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0, depending on whichever direction it would be. So the only thing we got to be careful is we don't want to use the word up as coming out of the page or down as going into the page. We want to just keep it simple as being up and down as being north and south, and then in and out as being into the page or out of the page. Okay, so our first hand rule then we're going to use to figure out how Oersted did his calculations or came up with his law or rule. So if we have a straight wire that's going to the right, so let's suppose our current's flowing to the right, we're going to use our left hand to figure out which direction the magnetic field is. Because we're using left hand, because it's negative current, so what we want to do is we want to point our thumb in the direction of the current. So we're going to point our thumb to the right, and then if we imagine like grabbing onto this wire, our fingers would curl around it. So our fingers would go sort of upwards and around the back side of it. Okay, so that's going to indicate our magnetic field. So if it's negative, thumb goes to the right, our fingers curl around it. So our magnetic field goes up and over the wire. So at the top of the page, our magnetic field would be inwards, right? So if we're going straight above the wire, our magnetic field will be going into the page. At the bottom, it'd be coming out towards us. And right in front of the wire, it would be going up, and then the back of the wire would be going down. So you get the idea of how it's kind of going circular around there. So the example at the bottom of this page works the same way, except our wire now is going in or out. So our wire is the circle, and it's showing that the current is going into the page. So you point your left thumb down into the page, and our fingers then curl around it in a counterclockwise kind of direction. Okay, so that means then for this question it's saying, what is the direction of the magnetic field? Immediately to the right. So if we're at the right, our magnetic field is going up. Above the wire, our magnetic field is going to the left. If we were going to the left of the wire, it'd be going down, and at the bottom of the wire, it'd be going to the right. So you can see it's just going around in a circle in a counterclockwise fashion. The second hand rule is just basically a modification of the first. And what it is if we have a straight wire, we get a round magnetic field. So the opposite logic is what happens if we have a wire that's going around in a circle, then our magnetic field is likely going to be straight. So if you imagine grabbing onto the wire, sort of like being a steering wheel, so your left hand would be on the left side of the steering wheel, your thumb is pointing up the way I drew the arrow. So you'd see that your fingers then would curl around the steering wheel and they'd be coming out of the middle. Right? Your fingers would go out through the middle, so we'd have a magnetic field going outwards. If we changed it and we grab it onto the top, so if you move your left hand to the top of the steering wheel, your thumb would be pointing to the right, your fingers would still curl around so that they'd come outwards. And if we moved our left hand to the right side of the steering wheel, your thumb would be going down, but your fingers would still curl outwards, and at the bottom it's kind of hard to do because your arm would be upside down, but you kind of get the idea. Or just sort of put your thumb at the very bottom pointing to the left, your fingers would still come outwards. So you can see no matter where we are on the circle, if our thumb is pointing in the direction, our magnetic field is still up through the middle of the circle. So when we get questions where they talk about a coil of wire, and that's usually used when it's a solenoid, and it's basically, a solenoid is just a fancy name for an electromagnet. So if we run current through the wire, that's going to turn that chunk of metal into a magnet. Because if we have all the magnetic field pushing the same direction, it's going to act just like a magnet does. So quite often these kind of questions are going to ask which way is north and south for that magnet. So we usually draw the coil spaced out just so it's easier to see. So let's suppose for this one, our current is going downwards. So our wire would be going down, so we could use our first hand rule, point our thumb downwards, our fingers would wrap around, and our magnetic field would go in this direction. And if we know our magnetic field's in that direction, that means we know that that end would be north, and the other end would be south, because that's just the way north-south magnetic fields work. Okay? The second hand rule then, like I said, is just a modification, and some people like it better because it's just a little bit more easy to manipulate your hand. So we just trade our fingers and our thumb around. So first hand rule, our thumb was the direction of the wire current, and our fingers were showing you the magnetic field. So for the second hand rule, we just do the opposite. Our fingers wrap around in the direction of the current. So imagine wrapping your hand around the way the wire is going, and your thumb then points to north, or points in the direction of the magnetic field. Okay, so that's kind of what the second-hand rule does. It just says wrap your fingers around, your thumb points to the north. So either way, it really makes no difference how you want to figure it out. So let's do one more example. So let's suppose I have a cylinder of metal, and let's suppose we're going to wrap it around with wire. So we're going to put the wire around, and I'm just going to draw one loop. Okay, so our wire goes around it like that, so it makes sort of like a steering wheel type shape. But in reality, right, a coil of wires would just wrap around and around and around. It'd go around hundreds or thousands of times. But we don't want to make it complicated, so we're just going to think of it as one wire coming down. So just picture one wire wrapping around and going around in a circle. And let's suppose the current comes downwards. So in this case, whichever hand rule you'd use, put your current going downwards, and we'd see that our north pole, our magnetic field, would point to the left, right? Our thumb points to the left. So that means our magnet then has to be north on that end, south on that end. Okay? If we had the same situation, except our current was going upwards, so you'd wrap your fingers upwards, and your thumb would point the opposite way. So current going through a wire is going to tell you which direction the north and south pole of the magnet is, or vice versa. If I gave you a question where I tell you that we have a certain magnet direction, so let's suppose we draw our magnet north and south like that, and I'm going to wrap some wire around it. So let's suppose our wire goes around the coil something like that, and I'll draw a few of them this time. So the question then would be, which way is the current going? If that north is up, which way is the current? So we can still use our same rule, just kind of do it backwards. So our current's going up, so our magnet's going up, so our thumb would point up, and our fingers would show the direction of the current, which in this case would be around it like that. So you can use the two rules either way to help you figure out either the direction of the north or direction of the current flow. And that's all for today.